So for the final video of the last lecture of the week, I wanted to do a few example problems. So we have 4 different examples here that just cover some concepts that we talked about in this lecture beyond the little mini examples that we did within the lectures. First says to write a sentence describing each of Newton's 3 laws. And we're not going to write detailed sentences on the DocCam, but just pause the video and think about it for a minute and see if you can come up with your own definitions. So remember that Newton's first law was the law of inertia. And you probably had that traditional definition of it, that a body at rest tends to stay at rest. But remember, kind of the more formal definition that we use is if there is no resultant force acting on a body, then the body, and my pen is dying here, so I'm going to swap it out. Sorry about that. The body's velocity will not change. Another thing that you could have written there is that the body won't accelerate, because remember that acceleration by definition is just the rate of change of the velocity. Resultant force is nothing more than the sum of all forces. And velocity is nothing more than how quickly, let me actually write it formally here, it's the rate of change of the position. And we'll say think speed, because the speed is actually defined as the magnitude of the velocity vector. So velocity is actually a vector, but it's the magnitude of speed. So that's Newton's first law of inertia. The second law is just F equals ma, which just basically says if a resultant force F acts on a body, the body will accelerate inversely proportional to its mass. So that's that the symbol alpha in mathematics oftentimes is meant to represent proportionality. So if you have a resultant force, or if all the sum of the forces acting on a body is not zero, then you're going to see an acceleration, and the more mass you have, the less the body will actually accelerate. So the third law was the idea of an action. Usually I wrote reaction first, but usually write it as action reaction pairs. And I'm just out of the, for purposes of time, since my writing is so bad anyways, because I'm trying to rush, I won't actually write that down. That just says that if two bodies exert contact forces on one another, if body one exerts a contact force on body two, then body two exerts one on body one, equal magnitude, opposite direction. So 2 here, compute the weight of an object with a mass of, so I'll write that down. So we're going to be given that the mass of an object is 20 kilograms. And remember that that's a scalar quantity. If we want to find its weight, which is a vector quantity, we can always compute the weight of an object, or approximate, I should say, by taking its mass and multiplying by the acceleration due to gravity. And remember that in the SI system, the magnitude of gravity is about 9.8 meters per second squared. Sometimes you see 9.81 used. And the direction of gravity is going to be towards the center of the Earth, which basically for all practical purposes for us just means down towards the floor. So if the body has a mass of 20 kilograms, then I can approximate its weight by just taking the 20 and multiplying by 9.8. And it is way too late for me to try to, I don't know why, usually like at night my brain stops working. 196 there. Now, what are the units? Well, we could say that the units are kilograms times meters per second squared. However, we know that the definition of a kilogram times meter per second squared is 196 newtons. Okay. So key point there is that remember that weight is a force, and really what I've done here is this is the magnitude, and we'll just say usually when you're starting out, you just draw an arrow to say the arrow that this points, and we'll just say it's towards the floor. Really, it's towards the center of the Earth. But usually we're going to use a two-dimensional coordinate system, and we'll just call in 2D, we'll say that all of the actual gravitational forces point in the negative y direction. So the last thing that we wanted to do here, state the SI units of position, velocity, and acceleration. This is really just to give you some additional experience of thinking about what these mean. Remember that position, or where an object is at in space, if you have some coordinate system and you have a body here, You measure its position, SI, in units of meters. Velocity is nothing more in terms of, it's a vector that describes how this position is changing over time. It is the rate of change of velocity. So its position is going to be measured in meters per second. And then acceleration is just the rate of change of that. So it will be in meters per second. But remember, a more natural way to write that is just meters per second times 1/second, which is just going to be meters per second squared. So that's the SI unit of acceleration. And last example here, if we have a 2 Newton force and we want to convert that to pounds, how will we do that? Well, we're going to need a conversion factor. And if you go to our slide here, we know that, where are we at here? 4.448 newtons is equal to 1 pound. So usually the way that you show this in dimensional analysis is to take the original quantity you have, which is 2 newtons, and we're going to multiply by a conversion ratio where the actual amount in the top and the bottom is the same. They're the physical same thing. However, the units are different. And we want to get rid of newtons, and we want to go to something in pounds. So we need a conversion factor that relates things in pounds to things in newtons. So notice that 1 pound is equal to 4.448 newtons. And if I put the newtons of the conversion factor in the denominator, those will cancel. And I'll just get 2 divided by 4.448. And that is going to be approximately, 2 divided by 4.448, 0.4496. I'm just going to round it to, I'll just rather write it out to, let's do 4 sig figs, 0.4496. And that is going to be in units of pounds. So hopefully all of you have seen, hard to read there, some examples of dimensional analysis before, but if not, that's the basic idea. You use that concept of cross-canceling in fractions along the diagonal to get the quantity manipulated into the unit that you want. So we'll pick this up next week, and you'll get some additional opportunities to kind of dig more into this. And the big goal is we're going to do a lab where we actually do static equilibrium analysis of a particle, and you'll see that it's just basically the same thing that we did with the vector lab that we did this week.